Hello and good day. Thank you very much for joining us. So welcome here in the virtual web room of NTI Audio for today's webinar. Today we will talk about how to establish an amplifier test sequence with the FX100 audio analyzer. My name is Markus Becker and I'm assisted today by Peter Gantenbein. He is the project manager for the Flexus line and he will take care of your questions during the webinar. The topics that we have prepared for you start with an overview on typical amplifier tests and use cases. We will show you the system configuration that we have prepared here and then swap over directly to the practical presentation, which will actually cover the major part of today's webinar. We will consecutively summarize what we have shown to you and also provide some application hints and tips before we come back to your questions and provide the corresponding answers. I guess that the overall duration of the presentation should be in the range of about half an hour. When we talk about amplifier testing, we have to differentiate between two basic use cases. The first one would be typical in an R&D lab. There you are looking for in-depth analysis. You want to look for comprehensive, detailed measurements, specific measurements to qualify the characteristics, the performance of your amplifier thoroughly. So for that purpose, you need a number of different tests that you want to have at your hand on the same level and just pick the one that you prefer. Just two examples that we have prepared here. That is the level, for instance, that is required to create a 0.1% distortion at the amplifier, or the linearity of the amplifier, or for instance, plotting the power versus the THD. But can be many more other different tests. The second use case is when you go to a production line where you want to verify the correct operation of your amplifiers, of the manufactured amplifiers. So here we are looking for a fast quality check that verifies relevant parameters that give you a reliable feedback whether this amplifier, the tested amplifier, is working correctly or not. So typically we are talking here about frequency response measurements with or without load, distortion measurements, damping factor, or power at the load or the gain of the amplifier, signal to noise ratio, and so on. The setup you need for these tests is very simple. You see it here on this sketch. You just need to connect the Flexus audio analyzer with the amplifier and then add a load. Please notice we have here a new module shown on the sketch, the FXDF module, which has just been launched, released to the public. And this is a module specifically designed for D-class amplifier testing. DF stands for D-class filter. And the purpose of this module is that it filters out the upper frequency components that are typically generated by D-class amplifiers. These upper components are, of course, not audible to the listener of the music, for instance. They are beyond the 20 kilohertz band, but they have a heavy impact on measurement results, for instance, especially on distortion measurements. And in order to properly be able to execute an audio test, you need such a filter if you test D-class amplifier. You can see here on this schematic graph the typical behavior, the typical frequency filter curve of this device, but I don't want to go too deep into the details. Just keep in mind that this module is now released and available and we use it in our setup. So my overall test setup consists of this FX100 connected to the amplifier with the load. The device is controlled via USB from a PC, which runs under FX Control software. This software is free of charge and comes along with every FX100 audio analyzer. I swap over to this software And what you see here now is the hardware and wiring view. You start setting up your test in this view by adding the corresponding items that you have connected to your flexor. So this is a virtual wiring that you apply here, but it has a huge advantage. It ensures that you are correctly connecting the corresponding inputs and outputs of the flexors. For instance, here by activating this link of the input channel number 1 of the DF module to the analyzer, you make sure that you are measuring correctly the input of the board, which is the output of the amplifier. Next step, you set up your test, and let us start with a typical R&D application. So I want, for instance, to measure the linearity of my speaker, and then I want to establish a second test of something different. You're going to see that now in a minute. So the first thing I do, I take a look at the generator properties and I unmute the outputs of the generator. These outputs are by standard muted as soon as you open a blank project, just for security reasons. And now we can drag and drop the step sweep properties, for instance, to our worksheet. Because for a linearity measurement, we need an amplitude sweep. So we select here the amplitude sweep mode. If I want, I could now amend the frequency at which this amplitude sweep is executed, but I leave it here at 1000 Hertz. On the other side, I'm going to amend the start level for that amplitude sweep. Actually, I'm going down to -80 dB just by pressing the page down key on my keyboard here. And the end level, I would adjust, for instance, to then 10 dB. And in the end, I increase the number of measurement points to 50. So the next step I have to do, I have to add the measurement graphs. So I select step sweep level channel 1. I add this graph to the worksheet. And I add the second channel to the same graph. So let us execute a measurement so far. You can see here. This is the linearity test. Well, I am going to add now also a THD measurement because I also want to know the distortion measured in the same step sweep. I rerun it. So you can see here the linearity of the amplifier output, and down here the distortion over the same step amplitude step. I'm going to rename now my sheet and call it linearity. So later I will find that easily when I have added many more measurements. And actually I'm going to just add another one, and let me call that level at THD. So in here now I want to establish a test that tells me at which generator output level, which is the input level of the amplifier, at which generator output level I can achieve a certain distortion of the amplifier, at which level I get the 0.1% distortion. So for that purpose, I need the meter waveform properties here on my worksheet, because I want to adjust the test frequency to 7500 Hertz. And now I'm adding a regulator. This procedure of identifying the corresponding generator level is an iterative procedure, and for this we need this regulator that automatically executes this procedure. When you look at the properties of this panel, we can see here, for instance, we can define the target. We want to achieve a THD of 0.1% or expressed in dB, that would be minus 60 dB. You can see it here, minus 6 dB equals 0.1%. And we want to start this iterative process at minus 10 dB volt, and we want to say that the maximum allowed output level of our generator would be 6 dB volt. So for monitoring what is going on, we can add a THD measurement of channel 1. We are just talking about channel 1 right now. And we also add a level measurement of channel 1. Make this a little bit larger because this is our target, the 0.1%. We can express it here in percent. Now I run this process. Because I have defined the target in dB, it's also shown here in dB. So you can see with a few steps, the system has automatically identified an output voltage of minus 4.04 dB volt, which results in this distortion of the analyzer of minus 60 dB, which is 0.1%. And this would be now the input voltage of the Flexus analyzer, which is the output voltage of the amplifier. So this way we can add more worksheets, we can add more tests, and then you can easily select the one, pick the one that you just need according as you have prepared them. Let me briefly open a predefined project that includes some other tests to show you that. We see here the same setup with the iterative process to identify the generator level for a specific distortion. We have here the linearity sweep, but now we have added actually another graph. You're going to see that in a minute. So you can see here something went wrong here actually, because let me do it once again, please. Oh, wait. I think I know it. No, wait. Sorry, that was a... let me do it again. Yeah, that's what I was looking for. Seems that there was a problem before. Sorry. Well, what you see here now is the linearity sweep, this curve, and here you see the deviation of this measured curve from the ideal straight line that you would expect. So here you see the difference between the actual curve and an ideal straight curve. And here down here, the same as before, the distortion test. So this is another example, or here I have added a third sheet where I have plotted the total harmonic distortion versus the power of the amplifier. So this way you can compile your R&D test according to your demands and just select the corresponding tab and execute the measurement that you want to see next. So let us swap over to the other use case, the production test. And for that purpose, I'm opening a second blank project. First step, as before, I'm going to virtually connect my FX100 to an amplifier and connect the corresponding channels of the new DF board to the analyzer inputs of my FX100. So in this example, we want to establish a sequence, so an automated execution of several measurements and other actions, one after the other. Just that at the end, we can press the start button, and at the end, we get all the results according as we like them. So here we start by dragging and dropping the generator properties to our worksheet. Let me briefly make that a little bit smaller. I unmute the outputs as before, and here I just increase the generator output level to 4 dB volt. And in the glide sweep settings, I increase the bandwidth to the maximum, to the 80 kilohertz, and I reduce the duration of the sweep to 1 second. The next step is I want to add the measurements that I need, and here I want to start with a frequency response measurement where the load is disconnected from the amplifier. So for that purpose, I add a frequency response graph, measurement graph for the two channels. And now wait a second, it was one step too early. I first have to activate the sequence mode. And in the sequence mode, I create a new step. And in this step, now I add this graph with the frequency response measurement. Now let us take a brief look at the sequence. So far it only exists of a single step. So I want to add an instruction to the operator, we call it a prompt, to tell the operator that he has to disconnect the load from the amplifier. So that's the name of this pop-up window that will appear, and this is the instruction. Disconnect load from amplifier output. I confirm. Just the order does not fit. I have to move that instruction up. So the order of execution will be from top to bottom. So I start with this prompt, then I execute this first measurement, the frequency response measurement. I can just rename it. Frequency response amplifier no load. And now, because I know that my next step is frequency response measurement with the load connected, I can already now add the corresponding instruction. Connect load to amplifier output. And this instruction, of course, should be executed after the first measurement and before the next one follows. Okay, now I'm adding a second step. You see that automatically the active measurements are duplicated. But let's say I want to see the frequency responses now of this second measurement with the load connected. I want to see it in the same graph as the first one. So I close this graph and I just drag and drop again the glide sweep level measurements to this upper graph. And you can see here that these are the properties of this graph. You see there are 4 curves from step number 1. The frequency response, channel 1, channel 2, that was the step with the disconnected load, and step number 2, again, frequency response of the 2 channels, but now the load will be connected. So let me rename that second step, that second measurement as well. So I call it frequency response and THD with load, because aside of this frequency response, I also want to see the total harmonic distortion of the 2 channels. I'm still in the same step. You see it up here that is highlighted. So in here, I just add another measurement, the THD of channel 1 and channel 2. And now there's another measurement that I want to execute, and that is the signal to noise ratio. And for that purpose, I need the meter level result of channel 1. I put it over here. You see, by the way, S2 says still we are in step number 2. I swap that to the volt. And now for the signal to noise ratio measurement, I need a third step. And in this third step, I'm going to mute the output of the generator. I click on new step. It automatically duplicates all the measurements. I'm going to just close these 2 graphs, which I don't need anymore. But here's the meter level measurement of step number 3. I want to see that. But now in state number 3, I want to mute my generator output. So all these settings are saved by the system. It knows exactly which status of these panels here shall be applied according to the corresponding steps up here. Now the last thing I have to do, I have to add a calculation item because the signal to noise ratio is calculated from these two levels. So I call it SNR of channel 1. I add as first parameter the meter level measurement channel 1 of state number 2, that was the one with the active outputs, and I call it U active. And as the second parameter for my calculation, I add again the meter level of channel 2, but now state number 3, the muted state. And I call it U-mute. And now the only thing that remains to do is entering the formula that calculates the signal to noise ratio and assigning the correct unit, which is dB. So that is my calculation result. Now let us run this whole procedure so that you can see how it looks like in reality. I click on run. The first thing that appears is this message, disconnect load from amplifier. I do it. You heard it in the background. I have connected a loudspeaker here to my output of the amplifier, and now I reconnect the load. Well, I made a fault. You can see that immediately. There are lots of these arrows around. So what I forgot actually is when we work with glides, we need to adjust the sensitivity, the input range of the analyzer correctly. So let me get back to the first step. And for this input range adjustment, we have another regulator, the glide sweep range. I press run and apply. I do the same for the second step. Okay. So let us execute the whole sequence again. Maybe here I just change the THD result to %. Okay. Disconnect the load. Reconnect it. Yeah, that's what I wanted to see. You see the result is perfect. We have the frequency response. We have of the amplifier with and without load. We have the distortion results, and here we have the signal to noise ratio calculated from these two results. Now let me open another prepared project where I have some more measurements included, but which is basically the same basement. Looks pretty the same. Just one more graph for the damping factor. And here's some more results. Actually, we are talking about the voltage gain, the power at the load, and the damping factor, which I have added here. Let me first run that sequence. So here you see the results. I have added, just to go a little bit more into the details, you see the frequency response is pretty much the same with or without load. Here in the distortion plot, I have added 4 more curves, and these are actually the odd harmonics, just the odd harmonics, and down here the even harmonics of the two channels. And you can see immediately that the overall distortion is mainly given by the odd harmonics, whereas the even harmonics play a minor role for this overall THD result. And here we have the damping factor, which is a very good indicator for the output impedance of the amplifier. Then here we see the signal to noise ratio for the two channels. We see the power at the load. We're going to show you just the calculation behind that. We measure the level and square it, the voltage level, square it and divide it by the impedance of the load, which is 4 ohm, and this way we get the power result. And last but not least, the voltage gain. We use the load voltage and the generator voltage for calculating the gain of the amplifier, which is 8 dB. So let me get back to our presentation and summarize what I have shown to you. We showed you the three measuring methods of the FX100, the meter mode for typically single value results like gain, signal to noise ratio, or power. The glide sweep for the more comprehensive tests, frequency response, distortion versus frequency, and so on. And the step sweep, which is a solution for specific applications like here, the linearity measurement, which is based on an amplitude sweep. Then we showed you the FX control test procedures, regulators, how to find the correct generator level that creates a specific THD, or the input range adjustment for the glide sweep measurement. We showed you how to establish calculation items. Down here I just have summarized the formulas of these calculations items. These are single value results, and here we had the damping factor, which is a graphical result, and the sequences for the production testing. Some further hints and tips. What we did not show you in here because it would boost the scope of our webinar is how to establish individual tolerance limits for an immediate passed-failed feedback. We have actually shown how to do that in a previous webinar, which you will find on our website. You can look up over there. This is a pretty simple procedure how you can establish these limits. Same applies for an automated data export of the acquired measurement results, for instance, into a Word or an Excel document. This is also supported by the software and is part of such a sequence. And we can look up how this works in the corresponding webinar or tutorial video on our website. Then we have an built-in hardware auxiliary I/O interface in our Flexes, and that allows us to integrate the device into an automated environment. This is a very powerful feature in the Flexes. So this way, for instance, you could automate the connecting and disconnecting of a load to the output of the amplifier, or you could do many other things, triggering external devices or receiving external triggers from a PLC, for instance. So this is a very great feature to extend or to integrate the Flexes into an automated environment. The board that you see here is just an auxiliary device for connecting this interface to peripheral devices. By the way, this topic has also been covered in its own webinar in the past that you will find on our website. Well, I'm at the end of my presentation. If you have questions, please don't hesitate and contact us. We have a very tight network of skilled and experienced supporters around the world. Here you see just our subsidiaries. There are many more partners, and please don't hesitate and ask whenever you need support for your application or have a specific question. So I will say thank you and goodbye for today, and see you soon again. Bye-bye.